yesterday we started talking about related rates, and today we're just going to finish up the example that we left at the end. So we'll do the related rates conclusion. And then we're going to talk about linear approximation. And time permitting, we'll talk about differentials. Okay, that's what we're getting at. All right, so, and today I will put up a homework sheet which will give you some practice in doing all these things. All right, so yesterday we finished off with an example. And the example had a rocket ship which was blasting off into space, and we had a camera over here which is watching the rocket ship blast off into space. And we computed, for instance, the change in height with respect to time. All right, at a given height. So we said, okay, when the height was actually, I think it was 1,000 meters. Okay, so when this height was 1,000 meters, we computed that the velocity, when we knew the velocity is 200 meters per second. So did I get the numbers right here?
Yep.
Yes, so the velocity of the rocket is 200 meters per second when the height equals 1,000. Okay. And if we called the distance between the camera and the rocket x, then we computed the derivative of x with respect to t, which is the change of the distance between the camera with respect to time when the height is 1,000 meters. So we did that. And I left you with a question which was, well, if you look at the angle of elevation of the camera, and we call that theta, we can also ask, as this rocket ship is going up, how fast is that angle changing? Okay, fine. So, again, we knew the velocity was 200 meters per second, so we knew that dh dt, right? That's what we computed. The velocity is the change in height with respect to time. That was 200. And what we wanted at the end was dh dt. So we want, I'm sorry, I said dh dt. We want d theta dt. Okay, and we know dh dt. Oh, and also I should mention we've given the original distance from the camera to the rocket as 1,300 meters. Okay. All right, so we wanted to compute dh dt, and we had, right, we know dh dt. So what do I need to put in here?
d theta over dh.
D theta over dh, right? I take the numerator of what I want over the numerator of what I know. Okay, so this means that I need to write down some formula that has both theta and h in it.
Is theta is equal arctan.
This is, generally this is h, right?
Arctan b over a.
Okay.
I mean, which is b, which is h. A, which is 1,300.
Okay, so let's take it slow. Oh, Chris.
Can you do the tangent on that?
Okay, so we have the same ideas going on here. Hussein is suggesting how the arctangent comes into play. You're asking for the tangent. Okay, so what's the tangent of this angle? Right? Well, the tangent of this angle is the opposite over the adjacent, right? Because we have a right triangle here. You have the opposite over the adjacent. So it's h, in general, h over 1,300.
Right. We're looking for theta, right?
Yeah, that's right. So, but we can immediately write down the tangent of theta is h over 1300. Okay? Now, we could solve for theta. How would we solve for theta?
Arctan.
Take arctan of both sides. Right? Why? Well, arctan is the inverse function of tan. Right? Which means they'll cancel out. So I could get, right? I could do arctan of tan of theta. Right? And that'll equal arctan of h over 1300. Okay? And then this bit here will just be theta. Okay? There's an alternative. The alternative is to do nothing. Right? I can do this and I solve for theta, or I can do nothing. Yeah? Agreed? I can do nothing, no problem. You can't make me do something. Just like Colin can't make me vote. Right? Okay. Now, what's the advantage of doing something? Well, now you have this nice explicit expression. And if I take the derivative with respect to h, I get d theta by dh equals, well, the derivative of this. Right? But then I have to remember, of course, what the derivative of arctan is. Okay? What if I don't do anything? What do I have to do? Well, I have to take the derivative, okay, but I have to use the chain rule, right? Because or if you like, implicit differentiation. But that's not so bad. Okay? What's the derivative? But again, remember, I'm going to want to take d by dh for everything. If I take the derivative of both sides, what's the derivative of tangent of theta when I differentiate with respect to h? What's the derivative of tan?
6.
Secant squared. But can I stop here? No, I have to multiply by
D theta.
d theta by
DH.
dh. Right? It's the chain rule. Okay? Theta is a function of h. So if I take the derivative with respect to h, I can't just take the derivative here. I also have to multiply by d theta dh. Right? That's what the chain rule tells us we have to do. Okay? It's just like when we had y's showing up in the equation, and you took the derivative, right? You did the outside, and then you to multiply by dy dx, or by y prime. So that's what happens to the left side. And on the right side, what rule do I have to use?
Quotient.
Do I have to use the quotient rule for this?
No, it's 1 over 1300. So it's 1 over 1300.
H over 1300 looks silly when you try to do derivatives, but this looks easy. Right? It's a constant times h, right? Of course, the derivative of a constant times h is what?
Constant.
It's just the constant, right? So you just get 1 over 1300. Okay, so now if I divide, I get my dh by my d theta dh. And so I get 1 over 1300 secant squared theta. Okay, now this is going to be a problem though, because all of my initial conditions are given in terms of the height being 1,000, right? Yeah.
Hey, over there, when you divide by secant squared, does it go to the numerator inside?
If you divide, it goes to a denominator. I mean, if this was just something that was an a,
Yeah.
you'd get a divided by secant squared.
Yeah.
Okay, so it goes on to the bottom. Okay, now, I mean, it's not such a hard thing to figure out at when h equals 1,000 what theta is, right? But if you wanted a general formula, we would now have to use, right, this thing that we figured out for theta, right? We'd have to plug it in. Okay, but the nice thing is we didn't have to differentiate arctan, which half of you don't remember and the other half do remember, but incorrectly. So, joke, just making fun of you. Lighten up, everybody. I keep telling you, lighten up, but take this class more seriously. Okay, but lighten up. But take it more seriously, but lighten up. Okay, so I can write it, I mean, I can either evaluate this when h is 1,000, or I can just write in this general formula. Right, so we know theta is arctan of h over 1,300. Okay, now, if you really were curious about how this thing is going to evaluate, we could play the triangle trick, couldn't we? Remember the triangle trick with secants and arctangent, or you draw a triangle and you say, okay, the tangent of that angle is supposed to be h over 1,300, so that my opposite is h, my adjacent is 1,300, and solve for the hypotenuse, and then look at the secant squared. Do you remember this at all? Yeah? Okay. It's a nice trick. But, you know, at this point, we don't really need to do this so much because, I mean, we can just plug h in here, right? Okay. So, but if you wanted to write a nice formula, you could use our triangle trick. Okay. But we don't need to. We can just sit down and compute things. Although the formula should be nicer if you use the triangle trick.
Isn't it easier to use arctan
Arctan for what?
to solve this problem?
Isn't it easier to use arctan?
Yeah.
In what sense easier?
Easier, I mean,
Do you mean is it easier to take the derivative?
yeah, that way.
Only if you remember the derivative of arctan.
Why not?
Why not? I do, but
It's not that hard.
does everybody remember the derivative of arctan?
1 over 1 plus x squared.
I'm impressed that at least the people in the front row. But you know, the problem with knowledge is it tends to dissipate as you move backwards in the classroom. Sorry, that's just a joke because you guys are sitting in the back and, you know, I'm biased. I didn't mean you guys. You can do it either way. You should get the same answer. What's easier? I'm not going to argue.
I don't want to, I mean, like using triangle and this stuff.
Well, you don't need to use the triangle on this. I'm just pointing out if you wanted to make a nice formula, you could use the triangle. This might give you what's going on with the triangle method much faster. That's true, right? Okay, and we can do it this way if you like, and it doesn't bother me at all.
I just see my answer.
Yeah, no, I mean, it's just a question of what do you remember more easily? Okay, I mean, some people remember both. I remember both, but some people don't. And so, and the other nice thing is, when you stop here, you don't have to do anything else. All right, and if this became more complicated, it might be much harder to solve for theta. And so I just got in the habit of you get to this point, and then you automatically differentiate. And a lot of times it works out just as nicely as if you tried solving for theta first. Okay, but in some ways it's a matter of taste. Okay, there's no. I'm not going to say there's a right answer as to how to do it. Okay. Okay, so now we just plug in all the information. We wanted d theta dt when the height was 1,000. And so this is d theta dh when the height is 1,000 times dh dt when the height is 1,000. And so, well, d theta dh we computed, it's this. All right, and when the height is 1,000, just put 1,000 in for h. So it's going to be, what, 10 over 13 on the inside. So you get 1 over secant squared of arctan of, okay, it's 1,000 over 1,300, a couple of zeros cancel. All right, you get 10 over 13. Okay, and at this point, if you had a calculator, of course this is trivial. If you didn't, you could also use the triangle trick at this step to compute what this is. Okay. In any case, and if you did it using the arctan version, right, you probably already would have the triangle step built into it, and then it'd probably be easier to see what the answer is. Yeah.
What happened to the 1300 times secant.
Oh, 1300 is just missing. Okay. And then we have to multiply by dh dt when h is 1,000, right? But we actually knew that dh dt was constant, it's just 200. So I put that on top, and I cancel a couple zeros with the 1300. And so you get 2 over 13, blah, blah, blah. Okay. And so we can see that's how the speed at which this angle of elevation is changing at that precise moment. Okay.
It's the unit.
What's that?
The unit.
Oh, the units, of course. We want the units, right? So, of course, this is given in radians.
What? Per second.
So this is radians per, what are we in, second? So, that's the change in the angle. All right, any questions? You can see we basically do the same process every time, right? Write down what you want, write down what you know, put down the middle term, and that's what you have to find, right? And you have to come up with an equation that relates them, take the derivative, then plug everything in at the point. Okay, so the trick is just, how do I translate some word problem or world problem into this nice little expression we call the G? That's it. Okay, well, if there's no questions, then we'll move on to linear approximation, which, as I said when we talked about this on Tuesday, it's nothing new. We've really done it already. We're just going to see how to apply it to some rather trivial examples, right? But I'll try to at least point out that there are some non-trivial examples where this stuff gets used. So the picture when you talk about derivatives that we always come back to is the following. I have a curve, right, representing the graph of some function. I choose some point on the x-axis, call it A, and then choose the corresponding point on the curve, which is f of A. I draw the tangent line to the curve at that point. And of course, what's the slope of the tangent line? The derivative at A, right? So the slope is f prime of A. Now, as I move away from this point A, clearly this tangent line moves away from this curve. And the same thing on the other side. Right? If I keep extending this line, it seems to be moving quite far away from this curve. But if I zoomed in really close, this tangent line looks very much like the curve. Right? It's just like the Earth. Right? The Earth is, of course, round, roughly. Okay, but most of the ground looks pretty flat to us, right? Because, well, compared to the size of the Earth, we're really small. Okay, so everything looks flat. Well, of course, we're on a hill when you walk outside, so nothing looks terribly flat. But, right, if you zoomed in and you get a little ant going on the hill, it looks, even though it's going uphill, it still thinks it looks pretty darn flat, right? Okay, so that's just what's going on with linear approximation. Is you're saying, from far away, we can see that this whole thing is curved, right? And a line does not approximate it very well. But from close up, right, that curve starts to look very line-like. Right? And if you zoom in really close, it starts to look even more line-like. And if you zoom in really close, it gets very line-like. That make sense? Okay, good. Okay, so what that says is if we want to approximate a function, at least locally, so locally meaning in some small neighborhood around a point, right? Just a little interval around the point, then what we should do is draw a tangent line, right? Write down the equation of that line and just say, well, our tangent line there is going to approximate the curve. Okay? If you just want to go a little bit around A, right? Just a teeny bit this way, a teeny bit that way, you have a pretty good approximation just with a line. Okay? And lines are very easy, right? If you want to know how far the line's going to change by going over a little bit, that means you're running a little bit. It's just going to go up, right, by how much it rises, right? That is by the slope. Fine. So, okay, so we write down the equation of the line. Of course, we've done this several times already. So, the equation of the tangent line to f of x at x equals a is, right, well, we have a point and we have the slope. So we use the point-slope form. That says you do y minus, well, the point here is a comma f of a. So y minus f of a equals the slope, which is f prime of a, times x minus the x coordinate, which is a. And if I solve for y, I get y equals f of a plus f prime of a times x minus a. Okay? And of course, right, y is f of x. So this is saying that f of x, y isn't f of x, y is, we're talking about the equation of the line, but this function is supposed to be approximated by this line, so f of x is approximately equal to f of a plus f prime of a times x minus a, right, at least near a. Right. Of course, if you go very far away from a, then this line is a pretty bad approximation. Tom, you look confused. Is it grammatical?
No, sorry, I just spaced out for a second. How did you get from y equals to f of x is approximately equal?
Ah, okay. So that's the idea, right? So y equals is the line, right? And f of x, of course, is the curve.
Oh.
And so, of course, approximation is saying, right, this curve is approximated by this line. Okay, so why don't we do an example and see how this gets used. All right, so where's my nice examples I cooked up? Ah, very good. Okay. Good, good, good. So let's just do kind of a silly example. And when I say silly, I mean it's a really neat example that you can do this. It's silly because, of course, we all have calculators. But to show you examples that, it's not so easy to do on calculators requires a lot longer. So I have to show you an easy example, right, which motivated this kind of thinking. So let's look at f of x equals the cube root of x. Okay, nice, good function. All right, and we want to find the linear approximation of f at x equals 8. Okay. So when I say x equals 8, I mean let my a be the number 8. Okay, well, our formula tells us what we have to do. We have to find out what the function value is at 8, what the derivative is at 8, and what is x minus 8. Well, that's x minus 8. Okay, that's not so hard. Okay, so first, what's f of 8?
Cubes.
Cube root of 8. 2, right? What do you have to cube to get 8? You start with 2. As long as we don't allow complex numbers. Okay? Then we need to know f prime at 8. Well, we better compute f prime. Okay, what's the derivative of the cube root of x? Would it help if I wrote it like this?
1/3 x to the negative 2/3.
Yeah, that makes it much faster, doesn't it? Okay, so 1/3 x to the negative 2/3, or if we put it back in this notation, which is somehow easier to calculate with, is 1/3 cube root of x squared. Okay, so now what is f prime of 8? We'll see. If you plug in an 8, you do the cube root, you get 2. You square it, you get 4. You multiply by 3, you get 12. So 1/12. Okay, this isn't so bad. This isn't so bad, right? This tells me, right, that f of x, which is the cube root of x, so let me write it like that. The cube root of x, all right, at least near 8, is approximately equal to, let's see, f of a, which is 2, that is f of 8, plus a 12th times x minus 8. Which, okay, I can simplify this a little bit. Let's see. Okay, I'm going to get a 12th x out. All right, maybe I can write that as x over 12. And then I have, let's see, minus 8 over 12, that's minus 2/3. Then a 2 is the same as 6/3, so 6/3 minus 2/3 is 4/3, so plus 4/3. So that's pretty cool, right? If you're looking for points around 8 and you want to say, what's the cube root? You don't have to do any cubing, right? You don't have to say, well, what if I want to do, say, 7.95? What's the cube root of 7.95? I mean, how would you even begin to do that without a calculator? You take a guess. Well, you say, well, it's pretty close to 8.
Yeah.
I mean, 7.95 is, so it's got, the cube root should be pretty close to 2, right? But how are you going to do that, right? What's it going to equal? Well, I'll tell you what it equals, roughly, because I put it into my calculator back in my office. It equals, well, I won't give you all the decimal places. 1.995824.6. Okay, so it is very close to 2. Okay, but, you know, for instance, let's say you were flying a rocket somewhere and you needed to know, you know, some sort of angle that came down to the cube root of 7.95. Would you like to know that it's pretty close to 2, or would you like to know what the angle is to 4 or 5 decimal places? You want precise calculation. Okay, well, what happens if, and so let me call this function here, okay, because it's the linear approximation, I'll call it L, and some f, right, because it's the linear approximation of our f. Okay, so what is LF of 7.95? So what is our approximation? Okay, well, of course, you just have to plug 7.95 into here, divide it by 12. Okay, this you can do by hand, right? You can do that on paper. It's just long division, yeah? 7.95 divided by 12 plus 4/3. Okay, of course, you can write down 4/3. You know it's going to be 1 1/3, so it's going to be 1.3333 repeated. Right? And what does this come out to be? Right? Well, the 3 repeated shows up, so that's pretty nice. It's going to be 1.99583 repeated. Okay. So they agree all the way up to the 5th decimal place, at which point they become off by, you know, just a little bit. Okay. So that's a pretty darn good approximation, just to divide. Just to divide by 12 and add 4/3 to find that cube root. I mean, did you guys watch Apollo 13, the movie?
No.
Oh, yeah.
Yeah, you remember they're up in space, and at one point they have to start doing all these computations by hand because all their computers are down. All right, it'd be pretty handy to know this kind of thing in that situation. All right. Okay, so there's a nice, just kind of silly example. Let me tell you about another example. So there's of course a branch of, well, I guess it's part of physics called optics, right? Okay, so I happen to appreciate this theory mostly because without it I can't see you. You all are just a big blur to me. So you'll notice, of course, that I have these wonderful glasses and they have these lenses, right, which are curved, and it's very similar to my eyeball, right, which also has this really nice curve to it. And if you take my eyeball and you rotate it, it doesn't really, I mean, of course, I'm not asking you to pull my eyeball out or anything. That's really sick, guys. I know this is Halloween, season and all, but come on. No, let's say if you took an eyeball out, right, it's a ball, it's a sphere, right? And if you rotate a sphere, it pretty much looks the same. I mean, other than, I actually have characteristics on my eye that you might be able to tell that I turned it, but if you forget about it, you've got a clear ball. Right? If you turn it, you can't tell that it's been turned, yeah? This is called rotational symmetry. So, let's say I draw some nice curve, right? This would be my lens. Okay? And, well, for instance, this lens, there's a very special line that goes through it. It's supposed to be a line. Okay, and it kind of goes right through the middle of it. Okay, and this is kind of the axis of symmetry, right? If you rotate around this axis, right, everything looks kind of the same. Okay, and this is called the optical axis. And so there's a branch of optics called paraxial optics. Paraxial optics. And it's very much interested in what happens when you have light coming in at an angle into this lens, where the angle is very small compared to the optical axis. Right? So there, this angle with the optical axis is pretty small. Okay? And you see what happens to the light. Okay, so this is interesting, right? Because the light's coming in from a lot of different places that are very, very close to my optical axis. Okay, so they study this. And they try to come up with all sorts of nice equations which are going to describe how light's going to reflect and bend and all sorts of fun stuff, and you want to know what's going on. Fine. What do I have here? What kind of nice object have I created?
Right triangle.
A right triangle, yeah? That's this nice right angle. Okay? And when I have right triangles, what kind of functions are going to naturally show up?
Sine and cosine.
Sine, cosine, right? Trigonometric functions. Right? If you see right triangles, there's a good chance trig functions are sitting somewhere near it, especially if you're trying to study something. And of course, trig functions all automatically make things harder to deal with. Okay? But what if we could approximate the trig functions by lines? Right? Then we could rewrite all these equations that show up when you're dealing with these things without trig functions. Right? You just have lines. Okay, fine. So how would we do that? Well, we just use the same theory. Okay, so let's start with sine. Let's say that f of x is, let me do theta, because we're talking about angles. Okay, so f of theta is sine of theta. And I want to write down a linear approximation. So I want to find the linear approximation of f at theta equals 0. Okay, because these are supposed to be very small angles, so I might as well do things near 0. Okay, well, what do I need? What information do I need to find the linear approximation?
Line, derivative.
I need a point and a slope, right? Yeah, okay, the point, right, is when theta is 0. Okay? So the point is 0, f of 0. Okay? So it's just over here, right? We looked at 2, we looked at 8 and f of 8. Okay, so that's our point, 0, f of 0. And what is f of 0? Well, it's sine of 0. What's sine of 0? 0, excellent. So that's very nice, right? Our point is 0, 0. This is going to make it very easy to do point-slope form. Okay? And what about the derivative? Well, what's f prime of x, or theta?
Cosine theta.
Cosine theta. And so what is f prime at 0? 1. Very good. Cosine of 0 is 1. So what? Well, here, replace f of theta with sine of theta. That looks good. What is sine of theta approximately equal to around 0?
0.
Let's see, it's f of 0, which is 0, plus f prime of 0, which is 1, times x minus 0. Okay, that's what the formula tells me. That's what point-slope form tells me. Of course, there's a lot of simplification I can do here.
Just x.
It's just x. All right, or, well, I used x, right? Of course, it should be theta. So it's just theta. So that's really cool. This says that near 0, sine of theta is just theta. So everywhere I see it, I write down formulas, right, for what's happening to this light as it's coming in near the optical axis. And every time these formulas involve a sine of theta, since this angle is close to 0, I just replace it with theta. That really simplifies things, and that really helps. And it allows for a whole theory called Gaussian optics to come about, because you have this. I wrote down a couple of angles just to give you some sense for how close these things are. So for instance, let's say you go as far away as 10 degrees. Okay, so what's 10 degrees? What is that? That's pi over 18 radians. So if you do sine of pi over 18, and this is equal to roughly 0.173648. And if you just look at pi over 18, this is equal to 0.174532. So this is already quite a bit away, right? This is 10 degrees. Okay, that's really quite a bit actually. Right? So within 10 degrees, it's even closer. Here you see it's less than 1/1000th off. Okay, but if you get even closer to 0, it gets really, really close. Okay? But even if you go far away, you're not too far off. All right, let's say we go up to 20 degrees, right, which is pi over 9. Hope I got that right, otherwise I'm going to look silly on video. All right, this is roughly 0.342. It goes on. These all go on, of course. Right? And pi over 9 is roughly equal to 0.349. All right, so it's getting further away. Okay? It's getting worse. Now it's 7,000 off. Okay? But that's actually still pretty good. I mean, if somebody said, what's sine of pi over 9? If you could compute pi over 9, you'd at least be right to 2 decimal places. That's not bad, right? What if you go to 30 degrees? Okay, so that's pi over 6. Okay, well, what's sine of pi over 6? Root 3 over 2, or is it the other one? Or is it the other one? Oh my goodness. Okay, so we're
Wow.
guessing. Good,
I
good.
just put all three out there. It's gotta be one.
Who showed me the hand trick?
We can find it.
How did the hand trick work?
Yeah.
Okay, what is it? Pi over 6. Hold on, I got sine 1/2.
Very good.
There you go.
All right, so it's 1/2 when we write it as 0.5, right, which of course is 0.5000. And what actually is pi over 6? Right, well, it turns out it's roughly 0.524. So you can see now it's really starting to get bad, right? Although you still write at least to one decimal place. So it's not a bad way of approximating, sine. It's just, well, forget that you have a sine to compute the angle. It's not that bad. Okay, now, why is this all working? Right? Well, we actually did this problem already. We actually talked about this already. Does everybody remember that? That we actually talked about this whole concept that sine near 0 is actually just approximately equal to the angle?
Limit.
Yeah, when we talked about the limits. When we computed the derivative of sine, you may recall we had to go back to the limit definition. And we got stuck. We got stuck on a certain limit. Namely, the limit as h goes to 0 of sine of h over h. And we had to do this elaborate geometric argument. We did it on this board right here. We had this elaborate geometric argument to show that this was equal to 1. Right? And what does that mean? That means that as h goes to 0, these two quantities get closer and closer to each other. Right? That's what it means. If you divide two things and you get 1, it means they're the same, right? Okay, well, if the limit is 1, that means that they're getting closer to each other. So sine of h gets very, very close to h as h goes to 0. Right? So we already proved this. Okay, so this is just a different way of saying. Yeah, I keep worrying about that as being 20 degrees times 2 pi over 360. That's 40 over 360. Yeah, it's pi over 9. I don't know why I'm so worried about that. Okay, well, when we computed this limit, we also had to end up going and computing a different limit. Which was what? The cosine of h, what was it, minus 1? Or no, cosine of h over h? No, there's supposed to be a minus 1 in there, right? And what did we compute this to end up equaling? Yeah, this is supposed to be 0. I feel bad about this. Yeah, it's okay. Okay, fine. So what is this saying? This is saying that as h goes to 0, okay, well, maybe it's not so easy to see what it's saying. Right? What's happening in cosine? We know cosine is going to 1, you get 1 minus 1 is 0. Okay, so this top part is somehow getting very, very small comparatively. Okay, so we did this, but maybe that doesn't help us to see what's going on. But if we do the derivative, we see it immediately. Okay, what's the derivative? Say theta. What's the derivative of cosine of theta?
Negative sign.
Negative sign. Okay. And what's negative sign of 0?
It's minus 0, which is 0.
To 0. Okay. So if we were going to do the same computation and find the linear approximation for cosine of theta at 0, all right, what are we going to get? Well, you're going to get 0, and now what's f of 0? F of 0 is going to be 1. Right? So you're going to get a 1 instead of a 0 here, plus, well, the slope is now 0. Okay? And it doesn't matter what I have here. It's not just 1, it's going to be a 0. The slope is going to be replaced by 0. Let's write it out, because it's probably too esoteric, abstract, or I'm using the wrong word. Too confusing if I don't write this. Okay, so if f of theta equals cosine of theta, then first f of 0 is 1, right? Because cosine of 0 is 1. And f prime of 0, right? We just computed that to be 0. And so cosine of theta, well, is approximately equal to what? Well, 1 plus 0 times x minus 0, right? Which is 1. So around 0, this function just looks like 1. Okay? That means, that's not, well, let's look at the graph for a second. Well, let's see. Well, if we draw the tangent line, what do you get? The horizontal tangent, right? And what point is this at? This is at 1, yeah? So of course, that's why the linear approximation is just 1. So around 0, you just say it's about 1. All right? So it's somehow not so nice, right? Because it's not telling you, as you move away, you say, well, it's certainly not going to stay 1, but boom, there it moves down. All right, what else do we got? So, well, let's do a real easy one, as long as we have these two already done. Find the linear approximation for tan theta at theta equals 0. And do it using my rule about trig functions. All right? What's my rule about trig functions? Once you've done something for sine and cosine, don't do it again, right? Just bring it back to those, right? Tangent of theta equals what?
Sine over cosine.
Sine over cosine. And so this should be approximately the same as, well, cosine of theta is approximately equal to 1. Sine of theta is approximately equal to theta. So tangent is also approximately equal to theta, near 0. Remember, okay, you get these nice vertical asymptotes, and it looks like that. So near 0, it looks very similar. However far you go out, that's about how far you go up. Okay, as you go away, of course, it's not true, because this is, for instance, right, pi over 2, and it's going up to infinity, right? So this gets bad really quickly. Okay. If we wanted to do this directly, right, well, what would we have to do? We'd have to take the derivative. Of course, it would be secant squared. We'd plug in secant squared of 0, which is the same as 1 over cosine squared of 0, which is going to be 1. All right? And so you'd end up with exactly the same equation as you had for sine. Okay? So, okay, it's really not that complicated, right? You just find the equation of the tangent line, right? And plug in a couple points. That's all it is. Right. Any questions on linear approximation? Let's see. How long do we have till?
15.
15. Oh, okay. What's that?
It's time to go already.
It's time to go already? Oh, okay. Okay, let me see. What else? Other examples I have. Okay, that's enough of those, maybe. Let me tell you about differentials now, because they're related to linear approximation. By the way, I mean, you see this 0, which is showing up. This is exactly where the slope is. same thing as that 1. Okay, so let's get a new piece of chalk. So, I've been promising you that when I write down something like dy dx, I said this is not a fraction, right? You can't treat it like a fraction. But I always said as just a little side note, but later on we'll see how you can treat it like a fraction. Okay? That's what differentials is going to be about. So, for the next 20 minutes, I want you to forget that we've used the symbols dy and dx and dh and dt and d theta and so forth. Okay, just forget that. Okay, they have no meaning to you right now. Okay, everybody raise your hand if you understand. Boy, that's pitiful.
I forgot what you said.
Forget that you know dy dx, right? None of these symbols mean anything to you, right? I've never talked about them. Okay, does everybody understand? Raise your hand. Do you understand? Shirley, you don't understand? Well, then why don't you raise your hand? Okay, very good. So, you don't know anything about them. The only symbol you know for the derivative, right, say of f is f prime. Okay, you know about derivatives, but dy dx means nothing to you. Okay, I'm going to define a new variable today. So, let's start with, we'll let y equal some function of x, and I'm going to define an independent variable, Okay, remember, do you guys remember the difference between independent variable and dependent variable? So, x, I can put anything in for x, yeah? If I have some function, y equals a function of x, I can put anything in for x, as long as it is in the domain, but in any case, it's an independent variable because it's independent of anything. I can just put anything into it I want. On the other hand, once I've put in x, I know what y is, right? Can I put in, if I put in something for x, can I just randomly put in something for y?
I'm drooling because I'm asleep.
Come on! Can I put in something for y if I put in something for x?
No.
No, right? Why? Because y is dependent on what I put in for x. Okay, so that's why we call it a dependent variable. Right? Because it depends on x. Okay? So, but I'm going to define an independent variable. It has nothing to do with x or y. Okay? And I'm going to call it dx. Okay, normally we give independent variables one-letter names. Okay, that seems to be the way we do it. Okay, statisticians don't do it that way. Computer programmers don't do it that way. But in math, we tend to do it that way. Okay, but here I'm going to give my independent variable a name with 2 letters, and it's called dx. Okay, which you've never seen this sort of thing before. Okay, so I know it looks a little weird. I'm also going to define a dependent variable. And I'm going to call it dy. Okay. What is it dependent on? Take a guess.
Yes.
Dx, very good. What is the relation between these two? Well, if I'm claiming dy is dependent on dx, I have to give you some relation, right? Tell you how it's dependent upon it. So the equation which is going to relate them is the following. If I want to know what dy is, okay, you tell me what dx is, and then multiply by the derivative. Okay, f prime of x. This is the equation which relates to variables. As a corollary, of course, these are variables. I can divide variables as long as they're not 0. Right? So as long as dx is not 0, I can divide by it. And then I get dy divided by dx equals the derivative of x. Okay? As long as dx is not 0. So I have these two variables, dx and dy, all right? And if I divide one by the other in this particular way, I get the derivative. Right? Okay, that's nice. Okay, so now if we wanted to, right, we could introduce new notation for the derivative. Right? Instead of writing f prime every single time like we have in this class, we could have written dy dx for the derivative. If only we'd have known about this earlier, but unfortunately, you didn't know about it before today. Okay. So let's see an example, how we use this. Well, actually, let's first see how this relates to our usual picture of the derivative. Okay, so again, I draw our canonical picture. Okay, so we have a curve. I pick a point. Okay, and I'm going to use some different letters for it this time to go with standard mathematical practice. I'm just going to write here x. And of course, what does that correspond to over here? But well, that's f of x. Okay. Now I'm going to draw my tangent line to the curve. Okay, and now I want to do the following. Normally when I moved over a little bit, what did I call that distance?
X plus h.
Yeah, right, I always went, the next point was x plus h, and the distance was h. I'm going to change that notation on you. Okay? Only because I not only need a change on the x-axis, I need a change on the y-axis. And I don't want to write h sub x and h sub y, because I think that'll confuse you. So instead I use the more typical notation. I'm going to go over a certain distance. And this distance is going to be denoted by delta x. Okay, so you can't see down there very easily. I'm writing a triangle and then an x. And this triangle is actually the capital Greek letter delta. Okay? You'll notice there's a theme of d's going on in this course. Okay? So this is a Greek letter. And whenever this letter is used in mathematics, you should probably guess that it means change in x. Okay? So some change. Delta usually means change. Okay? So down here, this distance is just the change in the x value. Okay? And so this point here is now x plus delta x. Okay? So the same thing as if I had an h. All right? I've just replaced it by delta x. The reason why I did that is I now go up to my curve, okay, and I get a new point. Okay, and what's the coordinate of that point? Well, if I go over here, it's f of what?
Of x plus delta.
X plus delta x. But I can, of course, also go all the way up to the line, and I get another point up there. I'm going to go straight up. I get a new point. Okay. Now, by changing x to go to x plus delta x, I change the function value from f of x to f of x plus delta x. Okay. And so this distance that I change, right, which is the change in the y value, what do you think I should call that?
Delta y.
Delta y, right? It's the change in the y value. So let me write this up here. Delta y is just the difference between f of x plus delta x, f of x plus delta x minus f of x. Okay, it's just this change in the y distance. Okay. Now, let's say I define right now my dx, right? This is my independent variable. I'm going to actually let it equal delta x. Okay, so whatever that little change in x was, I'm going to let that equal dx. What's dy? Well, let's see. Delta x equals dx, and dy is defined as, right, the derivative times dx. Now, what is the derivative at this point, x? Well, it's the slope of this tangent line. No? So that means that as I go from here to here, right, how far am I going up? Well, the slope of this line. So that's my dy. Get everything right? Yeah. Okay, so dy is how much, right, the y value changes not on the curve, but on the linear approximation. Right? So the difference between dy and delta y is your error. Right? That's how far off your approximation is. Okay? And what happens as delta x, which equals dx, goes to 0? Well, as delta x goes to 0, these points get closer, right? And what happens to my approximation as I get closer to this point? It gets... What happens to the approximation? Does it get better or worse?
Better.
It gets better, right? What does it mean that it gets better? Well, it means that the difference between the predicted value and the actual value goes to
0.
right? And if the difference goes to 0, that means that these two things,
Close to
they go close to each other. Right? So as delta x or dx goes to 0, right, dy goes to delta y, i.e. dy becomes approximately equal to delta y. Okay, now this seems like we're just throwing around symbols in a lot of different orders, you know, and then eventually saying, yes, but in the end they're all the same. Aha! Right, what have I done? Well, the reason why we do this is because it might be the case that computing delta y is not so easy. Right? For instance, you may know what f of x is, okay? Because maybe f of x is the cube root of x, and I tell you x is 8. And you say, oh, I know what the cube root of 8 is. It's 2. Right? But then I make delta x equal to 0.05. And you say, wait, if it's cube root of 8.05, I don't know what the difference is. Okay? I don't know what delta y is. So delta y is hard to compute in that case. Okay? But dy may not be hard to compute. In fact, it isn't. Because you can just compute the derivative and multiply by dx, which is actually delta x. Right, which you know explicitly. Okay, so maybe I do a quick example of this. Yeah, okay. Okay, so let's... Anybody who's ever come to my house knows that I have a lot of balls. I have 2 kids. Of course, I have a lot of balls. Why do you duck your head when I say things like that?
I'm tired.
Okay, good. Okay. All right, so let's say I have one of these balls, right? And we're going to assume that it's spherical, right? I have a spherical ball, and I'm going to measure it. And when I measure it, I measure the radius. And when I measured the radius, which we'll call r, I found out it was a very big ball. It's one of those workout balls that you can, you know, like the yoga balls, and you can kind of lie down on them and roll, right? Or you can get on one like this, where you can do all the Pilates stuff with it. Not that I do that sort of thing, but you know, occasionally I was. So it's a pretty big ball. Okay, now so here's the catch, though. I measured it to be 1.5 meters. The key word in that sentence is I measured it. Okay, I can't measure anything worth a darn. Okay, and so it turns out that at best, okay, I'm only accurate to within, say, 0.1 meters, because I just can't measure anything. Okay? So the possible error of my measurement is 0.1 meters, okay, which is pretty bad. Think about how bad that is, you know, but I've probably messed up like that before.
What's your confidence level for that?
What's that?
Since that.
100%. My possible error, it can't be any more than 0.1. Say I'm using a ruler, right, and there's marks on the ruler at certain points. Okay, and I know that, well, okay, I take a guess at where it is, but I can certainly see that it's between two of the marks. Okay, so I can definitely tell that it's within 0.1 meters, correct. Okay, so 100%, I can say that it's between those. Okay, fine. Here's my question. If the possible error of my radius is 0.1 meters, how bad could my estimate of the volume be? Right, if I use 1.5 meters to compute the volume, right, I'll get some number. How bad might my error be if I say, let's say I have the maximum possible error of 0.1 meters. How bad will my error possibly be? Okay. So, well, let's first write down the formulas that we know. We know how to relate the volume to the radius. Right? We did this yesterday, right? What's the volume?
4/3
Very good. 4/3 pi r cubed. Okay. Now what do we have here? Well, what could be the possible change in r? Well, the possible change in r could be 0.1 meters. Right? So I'll use delta r for the change in r is 0.1. Okay. And we'll at least, maybe it's approximately equal to, relate this to our new independent variable, we'll call it dr. Okay. Now we have this relation, v equals 4/3 pi r cubed, so we can also define dv. Okay. And we know that as long as r is reasonably small, this will be very close, right, to the change in volume, which is what I want. I'm looking, right, for this. Okay. So all I have to do is compute dv, and I have a formula to do so. dv is given by, well, the derivative of this function times dr. And what's the derivative of this function?
4 pi r squared.
4 pi r squared. So if I want to know what dv is, I just have to plug all my data in. 4 pi 0.1 squared times dr, which is, I'm sorry, that's 1.5 squared, because that's what the radius is. Right? And dr is 0.1. Okay. And I worked this out, and it worked out to be equal to 2.827 cubic meters. Okay? Okay, so that's how, and of course dv is approximately equal to delta v. So how far off am I, right? Well, at most this much. Okay, well, you shouldn't have any feeling for what that number means. Okay, so let me give you a percentage error. So if I want to know how far off I am in terms of percentages, which is maybe easier to think about, okay, so my error as a percentage, right, this is going to be given by, well, you look at how far off you were divided by the total volume. Okay, that's how you find the error of something. Okay, you look at how much you're off by divided by, right, what the predicted value should be. Okay. And of course, this delta v is approximately equal to this dv. So we use that number, 2.827, and then we divide by what the predicted volume would be. And that, if you work it out just by plugging it into our formula, is 14.137. Okay. And, oh, I forgot, of course, you don't just want this number. You usually, if you want a percentage, you multiply by 100%. So times 100%. And this number works out to be almost exactly 20%. So I'm off by 20%. Now how far off was I on the radius if I was 0.1 meters off? Right? So this is error percentage of V. The error percentage of R, right? Well, this is how far off I was on R divided by the radius times 100%. Okay. I was off by 0.1. The radius is 1.5. And if you work this out, it's roughly 6.67%. Okay, so what did I get by this? Well, this says that when I measured this ball, if I was off by at most 6.67 or 6 2/3%. Okay, but when that translates to the volume, I'm actually possibly off by as much as 20%. Right? So the moral is, if you make errors in your initial measurements, those can oftentimes blow up, right? And if you try to draw conclusions from them, you could be way off. I mean, it's bad enough being 6 2/3% off, but to then be 20% off in your result, I mean, this is pretty bad. And I was asking my wife about this question last night because she designs quilts. And when she designs quilts, every time she does it, she'll start off and say, gosh, I was only a millimeter off or a centimeter off when I was, designing something, and now when I put it together, it's like 6 inches off. Right? And so the same thing is happening, right, as we had in this problem, right? You make a small initial measurement error, right? And if you translate that error through a function which might blow up something like r cubed, you can end up with a really whopping big error in the end. Okay? And so this idea of differentials is a very slick, fast way of forgetting about linear approximations for a second and just computing things right out. Okay, we'll try to do another couple examples tomorrow, see how this plays out. I'm sorry, tomorrow, on Tuesday. And then I think before we do curve sketching, which is really the next big topic, I want to throw in something which I hadn't talked about on Tuesday, is L'Hopital's rule. Because I somehow feel you shouldn't leave calculus without having seen that at least once. But I'll put some homework up there for you to work on this weekend. And have a nice weekend.